Okay, so thank you very much to the organisers for this invitation to speak on signal generation and spatial encoding. So we're going to review some of the basic physics of signal generation. Hopefully some of these things will be familiar, especially after the first talk. And we're going to then start considering what the information content of case space is. And hopefully then this will give you a foundation, another look and understanding of that, so it will help you understand things like non-Cartesian case-based sampling orders and undersampling and so on in the future. Okay, so my financial declaration is I'm an employee of Philips. So when we put the patient into the MR bore, net magnetizations grow, and these are groups of spins that experience the same external magnetic field. We sometimes call them spin isochromats, iso meaning same, chromat meaning color, but we're just really referring to the fact that they, in that tiny space, experience the same external magnetic field. And for our purposes here, there's no real need to talk about individual spins pointing one way or another. We talk about these net magnetizations. So the net magnetization, which is the pink arrow in this animation, is tiny compared to the external magnetic field of the scanner. And so to measure it at all, we need to move it away from alignment. It gets swamped by the strength of the external magnetic field, and we have to move it away from alignment with that external field so we can measure it. So when we move it away, we flip it away from that alignment. And we do this with a circularly polarized magnetic field. And you can see that as the blue arrow here that's rotating slightly. And the nature of its rotation is to always serve to pull the net magnetization down towards what we call the XY plane, the orthogonal plane to the external field. And so it always tips it down. And when you move the net magnetization away from an alignment with the external magnetic field, it precesses around, it rotates around, which you can see. And that precession is the resonance of magnetic resonance imaging. So we're going to record what we're doing in the pulse sequence diagram. So here the red line's the RF pulse where we put the energy in, and then we start to be able to see, when we turn the RF pulse off, we see a signal decay, and we can detect that in a locally placed coil of wire. This is called the free induction decay. So we'll slowly build up what we're doing on this pulse sequence diagram. Now, in the laboratory frame you saw before, you could see the precession, but if we ourselves rotate the view that we're using to look at this movement of the net magnetization vector, if we rotate at the Lama frequency, you can see the mechanism of tipping this magnetization down is very efficient and very straightforward. And this is the rotating frame of reference, and that's the view we nearly always use to talk about MRI physics. It makes things much simpler to appreciate. But we'll go back into the laboratory frame of reference for a minute and see what happens when we turn the RF pulse off. And this is when we get a signal out. So we've put the energy in, now we're going to get a signal out. And this is when the FID occurs, because we see that the net magnetization relaxes back to the place it wants to be. That's the thermal equilibrium. But the way in which the net magnetization vector relaxes back differs from one tissue to another. And this is where we get our contrast from in MRI. And the vector component of this relaxation in the XY plane causes its own temporary oscillating magnetic field at the precession frequency, and we stick a receiver coil nearby, which is a coil of wire. We get an induction in this coil and measure a voltage. So back in the rotating frame of reference, we can divide this motion up into two vectors, the recovery part and the decay in the XY plane part. And these are both described by equations, and the time constants of those equations tell us how steep these curves are. And that you know this already. These are the relaxation times, the T1 and the T2, which differ between tissue types. Okay, so we've got a signal that's measurable, and we now need to start spatially encoding it. And we do this by the addition of linear magnetic field gradients. So when we turn on our RF pulse, when we put the energy in, we also apply a magnetic field gradient which limits the effect of the RF pulse to where the Lahm equation still applies, which is the imaging slice. Okay, let's see what we're doing with that on our pulse sequence diagram. And we just turn on the gradient in the slice select direction at the same time as we turn on the RF pulse. And then we get free induction decay from the slice, mostly from the slice that we've excited. But here's something we should always remember, which is whilst our gradients do something useful for us, signal encoding, they also cause dephasing. It's an unwanted side effect which we can use to our advantage in many cases, but in this case we just need to undo the dephasing effect. So we've used this slice select gradient to do some encoding, but it also causes some unwanted dephasing in the second half of that lobe. So we just reverse it with this little additional gradient. So to apply a pulse containing a narrow band of frequencies, we use a sync pulse envelope, and you saw this quite nicely in the previous talk, and that's because the Fourier transform of this sync pulse is a narrow band, a slice. And since the sync pulse cannot be infinitely long, we need some short pulses. You don't get a perfect slice, but it's approximated. Okay, so we've got a signal coming from a slice. And now we need to spatially encode that signal within the slice. And we do this by the addition of another linear magnetic field gradient. Let's consider frequency encoding. If we turn the gradient field on in the frequency encoding direction, then the precession frequencies immediately vary along that direction of the gradient. And we can, of course, detect these signals, and they all come together, all mixed up together. Let's just put this into our pulse sequence diagram. So here's the frequency encoding line. There it is. We turn on our gradient and we measure a signal at the same time. However, we saw, as with the slice select gradient, this gradient also does something annoying in this case, which is dephasing. So as we're encoding the signal, we're also spoiling it away and causing dephasing. So what we can do is add another gradient and pre-dephase in the opposite sense, so that when we measure our signal out, it comes to be completely in phase at the center of the signal that we measure. And this is why we talk about echoes in MRI, because we get the signal to come back in this way. And the center of the echo is when we usually record the most important signal information, and we'll see what that is shortly. Now, it's important to note that when we measure any signal in MRI, it always comes from the whole patient, or mostly the excited volume, but from what the whole content of what's inside the bore, and all these signals come mixed together. Now, you may already know that we can separate out these signals, these different precessional frequencies, using the Fourier transform. But before we talk about this, it's helpful to look at it in another way and consider the information content that we're measuring. So let's go off on a little aside here for a minute. Think with me about how we can separate the information content in an image. The information content in an image can be separated out in many ways, and then we can rebuild it with that information. And in this illustration, I've used triangles. Or we could use rectangles. Well, in MRI, we use waves. This is what I mean. On the left panel, you can see the example of the final MRI image of the knee. In the middle panel, you can see the data that we acquire to create that image. But on the right panel, you can see I've used just some of those data points that are used to create the image of the knee and added them together just one at a time. And you can see that each point is made of a wave that added together constructively and destructively interferes to start to form the image of the knee. We're going to look at this in a little more detail. So we call these waves spatial frequencies. You can sort of notionally imagine a wave in front of you in space, and they're described by their frequency and their orientation in space, and of course their strength or amplitude. And therefore it's convenient to use complex numbers to describe them with units of per meter to describe spatial frequencies. Now these spatial frequencies are not the precessional frequencies that we just talked about. So what are they waves of? To understand this, let's go back to our frequency encoding gradient. What happens at one position in the body to one net magnetization vector while the gradient is on? Well, it accumulates phase. And the phase measured in radians, accumulated by a particular group of spins, a net magnetization vector, is equal to the time of and the strength of the gradient that it's experienced so far. It accumulates phase depending on the gradient strength it experienced and for how long. So let's see what's happening. With this accumulation of phase. So what happens early on in this frequency encoding gradient? If we look at the screen, we can see that on one side of the body, precessional frequencies are faster, and so net magnetizations, their relative phase, they get ahead. On the other side of the body, the precessional frequencies are slower, and the relative phase of these net magnetizations lag behind. And some phase roll has developed. In this example, one cycle of phase roll has developed across space. This is a low spatial frequency. And then you make an instantaneous measurement, which goes into one k-space point. So all the signal is summed up from the whole body. The vector sum across the object goes into one k-space point. Okay, so far so good. Let's go later on in the gradient. What's happened now? Well, let's have a look. So by that time, a lot of additional phase roll has developed across space. More cycles of phase angle have evolved across space, and this is a higher spatial frequency. And again, we make a single instantaneous measurement at this moment in time. This goes to one k-space point. And we'll see later, this is the same effect is essentially true of the phase encoding gradients, which we'll come to later on in terms of what they produce, phase roll across space. So we've seen what's happening across the patient for the application of a gradient. So when we measure this instantaneous value, this single k-space point, what are we getting? We said before, it's all these signals mixed together. Well, the total momentary signal that we're measuring is where we're summing up all the isochromat vectors, the net magnetization vectors, from all locations in a slice, weighted by their spin densities, which is something we really want to know. This is how much is what's the spin density at this particular point in the body. Now, the mathematics of this equation, the form of this expression, tells us that the signal is the Fourier transform of the spin density in the sample, and therefore this is called the one-dimensional imaging equation. So let's continue thinking about this instantaneous MR signal, what we're measuring as we record a single k-space point. We saw that we're summing up all the net magnetization vectors, weighted by their spin densities. But what if all the, we saw that we're using a linear gradient, so if all the net magnetization vectors are equally spread around, because we're using a linear gradient, doesn't this all add up to zero? Doesn't it all cancel out? Well, perhaps, but also perhaps not. So consider a regular or regular-ish variation in spin density. Here I've just, the blue is tissue and there's some gaps. a regular variation in spin density which kind of matches the particular spatial frequency that we're interested in at this moment in time, that we're essentially testing against the tissue. If the tissue matches the phase roll quite well, then we get a higher value for this k-space point, a stronger signal for this spatial frequency. And all the spatial frequencies, all the different k-space points, are similarity measures of what we have in the scanner. So what then do we do with all these k-space points that we measure, all these different similarity measures that we're testing these spatial frequencies? And we saw earlier that the signal is the Fourier transform of the spin density of the sample, and so we use an inverse Fourier transform to determine the spin density, and we integrate over all these spatial frequencies. So we've seen that we take digital samples as the frequency encoding gradient is on, and this allows us to test different spatial frequencies and record their k-space values as they evolve during the application of the gradient. And notice that we could turn this gradient off if we wanted to, instantaneously, as we make these measurements, as you read out along the frequency encoding direction. And this is actually something that we do for 2D chemical shift imaging. We do this in two directions, and this is essentially phase encoding, turning the gradient off and leaving some phase roll, and then making a measurement, and then turning it on, producing some more phase roll, turning it off again, and making a measurement. This is phase encoding, and 2D CSI is essentially phase encoding in two directions. And there are scans where we use frequency encoding in two directions, and this will become clearer. So we've talked about how we decode phase roll in one direction, and in the orthogonal direction we use phase encoding, and frequency and phase encoding work together to produce these waves in space at any angle, and this allows us to draw any object. Okay, so let's take a moment and just add phase encoding into our pulse sequence diagram. Here's the phase encoding gradient. This is the pre-rewinder that we introduced earlier, and this produces some phase roll in the orthogonal direction to frequency encoding, and we read out some k-space values and put them into k-space as a pictorial representation of k-space. And then we repeat this many times, and we just do this at different phase roll, different phase encoding steps, so that we can fill up all these different k-space values one by one. And then a two-dimensional Fourier transform allows us to calculate the image, weighted by relaxation times and so on. So let's play with this a little bit. Let's try and understand the k-space point a little bit more. So here's the k-space. This is all the spatial frequencies. It's all sorts of angles and magnitudes. And if we do a 2D Fourier transform, which is the quickest way of doing this, you create the image of the knee. But here I've artificially inflated the value of one k-space point, and it's hard to see, but it's just there. Can you see that little dot? Well, that little dot represents that wave, that spatial frequency, that phase roll in space. Here's another inflated k-space value. Well, can you see it? It's just there. That's that spatial frequency. And if these waves, you kind of get this sometimes as an artifact, an RF spike artifact, for example, where a very loud, if you like inverted commas, a loud RF noise has occurred. So I don't know, static discharge on a patient's clothing, maybe the light fitting's not working, and it's like a flash of RF frequencies has occurred. So when you measure that particular spatial frequency, you measured way too high a value, and so you get this wave-looking thing across your image, and it just depends where you were in k-space, what particular spatial frequency you were measuring, depending on the orientation and the size of the wave. Here's this little increased k-space value. So you can see that the closer we are to the center of k-space, the larger the waves. The further out we go, the finer the waves. And if you just do a 2D Fourier transform on the central values in k-space, then you get mostly light and dark areas. You need light, big waves with big light and dark areas to draw, and if you like, the light and dark areas of an image. So you need the low spatial frequencies to draw the contrast in an image. Similarly, if you do a Fourier transform just using the fine waves, you can only draw fine detail. And again, you can see here, if I've added together the central 9x9 spatial frequencies, you can see the waves adding and subtracting from each other, interfering to start to form the image. So a little side note here, if you want to play with this yourself, then if you have an Android device, go and search for the wonderfully named KSpap, and you can play with removing parts of K-space. You can just do a Fourier transform on certain parts of K-space. You can miss out lines and simulate motion. Add an RF spike for fun. If you've got an iOS device, go to kspace.info. Got another very nice app that allows you to do these similar things to play around with, and gives you some more understanding of K-space. So in MRI, we're measuring spatial frequencies, and this is one of the differences between magnetic resonance spectroscopy and magnetic resonance imaging. So in spectroscopy, we are measuring the oscillations, samples of the oscillations in the time domain, and do a Fourier transform to get the frequency domain spectrum of chemical shifts. Whereas in MRI, we are sampling the spatial frequencies, and we put these in the frequency domain, and that's what we're putting into K-space. Then we do an inverse Fourier transform to get a assessment of what's in the scanner, the spatial object. So when we fill K-space, we can do it line by line, as you've seen so far, points on a grid. This is called Cartesian filling. It just means the points on a grid, after René Descartes from the 17th century. And this is the pole sequence we've seen so far already. And the order of the lines is up to your imagination. Sometimes we want to synchronize with physiology or motion or and so on. But as long as you acquire the spatial frequencies that you need. You might ask, well, why can't we just do frequency encoding in two directions? Why do we have to do phase encoding? Well, of course you can turn on frequency encoding gradients in two directions, but then you're not going along the grid and down a grid. And this is non-Cartesian filling, where such as a radial line, which is illustrated here, or a spiral, and so on. And again, non-Cartesian K-space trajectories are limited only by your imagination and your ability to control your gradients. In what order will you acquire these data? Do you need to consider the reconstruction complexity and the artifacts you may see? So we've got some propeller type acquisitions here. This is a cone in a 3D K-space, and some spirals, just for illustration. Okay, so when we've made our measurements, there are adjustments we need to make to K-space data before the data is ready to be turned into an MRI image using the Fourier transform. And one of these is K-space apodization, and this is where we smooth off the signals and reduce them at the edges of K-space. And this is because since we can't acquire an infinite K-space, we have a sudden stop of data at the edge of K-space. And this causes ringing artifact in image. And so smoothing off the edges of K-space like this does reduce the resolution by a very tiny amount and increase the SNR by a very tiny amount, but it improves image quality. And there's other things we do as well, which help us to improve image quality. And a number of methods are used during acquisition, which pair up with steps we take in reconstruction. So, for example, profile-dependent amplification. You can turn up the gain really high for edges of K-space, where the signals are small, so that we can sample those signals very well. Of course, we do some data reordering for negative measurement gradients, for example, in EPI. And in the EPI also, we have to do some regridding, because We want EPI to be as fast as possible. It's one of the fastest methods of reading out data, and so we sample on the slopes of the gradients as well as the plateaus of the gradients, and that's essentially a non-Cartesian bit of sampling. So we have to regrid those data onto a Cartesian grid to do the Fourier transform. ADC nonlinearity correction. I mean, nobody's hardware is perfect, so we make those corrections so that low voltage signals are not attenuated. And other corrections are made as well. So we actually introduce frequency variations and phase variations whilst we're acquiring data, because those variations will act differently on spurious signals versus on the true MRI signal. And then in reconstruction, when we remove the effect of those changes that we made, we're left with the true MRI signal, and the spurious signals are removed. And all these steps are taken to make it so that the raw MRI signal that we have before we create our MR image is as close as possible to a perfect MR system, which of course is impossible to make, but we can correct for the limitations of hardware that is made. So we've reviewed the generation of the MR signal, how we encode that signal. We've also seen what the data in k-space represents, these spatial frequencies, and some adjustments and corrections that are made to k-space data. And we've seen that these gradients allow us to move around the location, in inverted commas, of k-space, and to get some information that we can use to calculate the image. So when we consider k-space coverage, whether we're undersampling, how we're going to go through k-space to get this data, how efficient it is, reconstruction complexity, and so on, we're moving around k-space, and what we're really asking ourselves is, what spatial frequency will I measure? And I'd like to thank you very much for your attention.